Hello learners, we have already understood the concept of transfer function, then block diagram reduction technique for the purpose of derivation of transfer function of a complex system. Within this video, I am going to discuss another technique for the calculation of transfer function of a complex system, that is the signal flow graph technique. So what is a signal flow graph? It is a diagram which represents a set of simultaneous equations. It consists of nodes which are connected by directed lines, and those lines are called branches. Every branch has an arrow. What is that arrow doing? It is representing the direction of flow of the signals. And it's a very good choice for complicated system, because block diagram reduction technique sometimes becomes very tedious and time consuming, and sometimes you cannot judge that how to reduce that block diagram in the minimal way. So in such cases, in such complicated cases, signal flow graph technique comes out to be very helping. So what is the terminology? The first term that we come across in a signal flow graph is the node. Node is a point that is representing a variable. So whatever variable we are having within a particular system, those are represented by nodes within the signal flow graph. Like if we have the this equation, x2 is equal to t1 to x1 plus t3 to x3. It means there are three variables, x1, x2 and x3, and we'll be having three nodes, x1, this is x2, and the third one is x3 over here. Then branch, it is a line joining two nodes. So a line that is joining x1 to x2, it is called as a branch. Then there is the input node. The direction of the arrow on the branch represents the direction of the flow of the signal. Then input node, it is a node which has only outgoing branches. So in this, we can very well see x1 node signal is outgoing, to x2 node one signal is incoming, and another there are two signals which are incoming. So it cannot be the input node. So input node is the node that is having only outgoing branches. Then output node, it is the node that is having only incoming branches. So that we'll see later with the help of a particular diagram. Then transmittance, it is the gain between the two nodes. Like in this, x1 and x2 are two nodes. In between this, we are having a branch that is connecting them. And here you can very well see that T1, 2 is the gain the system achieves while traveling from x1 to x2. So this is the transmittance of this branch. Then we are having the path. It is the traversal of connecting branches in the direction of the branch arrows, such that no node is traversed more than once. So from the source node to the destination node, we just keep on moving in the direction of the arrows such that no node is traversed more than once, then we'll get a path. Then forward path, a path which originates from the input node and terminates from the output node, and along which no node is traversed more than once, is called a forward path. Then forward path gain. Within a forward path, we'll be having a number of branches. So each branch will be having a gain or transmittance associated with it. So the product of transmittances of all the branches of a forward path is called as the forward path gain. Then another definition is regarding the loop. A path that originates and terminates at the same node and along which no other node is traversed more than once is called a loop. So if we are starting from a particular node and while traveling in the direction of the arrow, we come back to the same node, then we'll say that it loop is traversed. And while forming a loop, whatsoever branches are coming in the path, if we take up the product of the transmittances of those branches, then we'll get the loop gain. Then non-touching loops are those loops which do not have any common node or the branch. So you can very well see over here, RS is the input node because it's having only the outgoing the branches. Then CS is called the output node because it is having only the incoming branches. Then within this we can have the loop. Loop is, we start from here, we go through this branch that is having a gain G2, we go through this branch that is having a gain H2. So this is a loop that is starting from from a branch, and it is terminating on the same branch. So starting from here, again we come back to this. This is also a loop. This is called self loop. It is starting from this branch, then we come across a gain equal to L2, then we come across a gain equal to H3, and we come back to the same branch. This is called self loop. Then also we can identify another loop that is starting from this node, and it is we come across a gain of G7, then we come across a gain of L3, we come back to the same node. So this is also a loop. So we can identify a number of loops. Then we can talk about the forward path. If we say a forward path between node RS and this node, it will be this to this. So this forward path gain will be represented by G1 to G2. So this is a path. This is not a forward path. Then in case we just take up a path from the input node to the output node, that will be a forward path. So a path that is starting from RS, then we travel across a branch that is having a gain equal to G1. Then we travel across a branch that is having a gain equal to G2. This branch having gain G3. This branch having gain G4. So G1, G2, G3, G4. This is the gain of this forward path. Similarly, if we just look at the another path, this is G5, G6, G7, G8. So this is also the forward path gain for a path that is starting from the input node RS and that is terminating on the output node equal to CS. Then while defining the forward path, we have to just take into account that none of the node should be traveled more than once. So like if I say this is the path from RS to CSS, having this branch, then having a gain equal to G6, having a gain equal to G7, then having a gain equal to H7, then G7, then G8. It cannot be a path because the nodes, this node and this node, while defining this forward path, are traveled more than once. So that we have to check that whenever we are defining a path or we are defining a forward path, then none of the node should be traversed more than once. So we have come to know these are the nodes, then these are the branches, these are the gains of the branches. Then we have discussed about the loop that starts from the same node and terminates on the same node. Path, that is the traversal of the path from the source node to the destination node. Forward path, that starts from the input node and ends on the output node. And the gains, product of the gains associated with the forward path, that are terms at the forward path gain, and product of the gains of the branches forming a loop, that constitute the loop gain. And we have just learned that what are the input nodes and what are the output nodes. So how do we construct a signal flow graph with the help of the algebraic equation? For that, just look at this. We are having these 5 equations which are representing the mathematical model of the system. So here we can identify that there are 6 variables: y1, y2, y3, y4, y5, and y6. So first of all, we'll mark 6 nodes: y1, y2, y3, y4, y5, and y6. So we'll represent all the equations one by one. So the first equation is y2 is equal to a1 to y1 plus a4 to y4. So this is y2. We have to consider only the incoming signal. To y2, incoming signal is a1 into y1. So it is represented. Then a4 into y4. So this is represented as a4 into y4. So to y2, 2 signals are coming, a1 to y1 and y4 to y4, and we just take the sum of them to get the value of y2. Similarly, y3, it is equal to a23 y2 plus a53 y5. So y3 is a23 y2 plus a53 y3. So similarly, we can represent the third equation, y4, this is y4, incoming signal to this is a34 into y3. Then similarly, incoming signal to Wi-Fi is A45Y4. So A45Y4 plus A35Y3. This is A35Y3. Then Y6 is equal to A56Y5. So this is represented by this part. So then we combine all these small parts together to form the overall signal flow graph of the system. So that is being shown over here. This is the overall signal flow graph. So this way, when we are having a mathematical model that is describing the algebraic equation of the system, then we can just take up each equation one by one, and then we can combine them together to get the overall signal flow graph. Then construction of the signal flow graph from the block diagram. So wherever we are having a summer, there we will be representing a node. So one node is here, another node is here, another node is here. Then at this point, we are having a takeoff point. Again, we have to assign a variable, and then we are having the output node. So wherever we are having a block, that can be represented with the help of a branch. So here we are having a block, it is represented with the help of the branch, and gain of transmittance of that particular branch is equal to gain of the block that is connected on that path. So it's very easy to get the signal flow graph from the block diagram that we have shown within this particular diagram. Then once we are having the signal flow graph, what is the use of it? Because we have till now we have learned a number of things, number of definitions associated with the signal flow graph. Then why do we draw the signal flow graph? And what is the benefit of drawing the signal flow graph? The benefit of signal flow graph is to derive directly the transfer function of the system model. And for that, the formula that is generally used is the Mason's gain formula. Mason's gain formula states that transfer function of a system between the input node that is representing the input variable and the output node, this is given as equal to sigma pk into delta k for all values of k divided by delta. Now, K is what? K is the number of the forward path. So within a signal flow graph, we have to identify that how many forward paths are existing. PK is what? PK is the kth forward path. So this is PK is the gain of the kth. So we'll first of all, we'll identify all the paths between the input node and the output node, and then we'll calculate the gain of each and every forward path gain that will be represented by pk. So in case there are two forward paths, then the value of k will be equal to 2. So in that case, we have to take up numerator as equal to p1 delta 1 plus p2 delta 2. Now, how to get the value of delta or delta k? That is another question. So delta is equal to 1 minus sum of loop gains, taking each loop one time. So first, then we have to identify all the loops within a signal flow graph, and then we'll take up the sum of the loop gain of all individual loop, and we'll just put up over here. Then we'll identify that there how many loops we can identify and how many pair we can generate of two non-touching loop. Then we'll just take up the sum of the product of the loop gains of two non-touching loop. Then minus 1 minus, then plus, then again minus. This is sum of the loop gains of three non-touching loop. So this is a minus, then again plus. This is the sum of the gain of sum of the product of the gains of four non-touching loop, and so on. This process will continue. Then this is the way we get the value of delta. Then how do we get the value of delta k? Delta k is is simply calculated as delta is calculated, but this is delta for that part of the graph which is not touching the kth forward path. Like we take up the first forward path, we just get the value of delta for that part of the graph that is not touching the first forward path. That will be equal to delta 1. Similarly, delta 2. So we have to calculate P1 delta 1, P2 delta 2 for all values of the forward path from 1 to k. We have to get this, and then we have to add them together to get the numerator. Then delta we have already discussed that how do we get the value of delta. So this is the Mason's gain formula that is used to derive the overall transfer function from the signal flow graph. So in order to get the value of the of a graph, value of the overall transfer function using Mason's gain formula, let us consider a basic closed loop type of the system having the GS as the forward path transfer function, HS as the feedback path transfer function, RS as the input signal, and CS as the output signal. So since there are, this is the this one, wherever we are having a summer or wherever we are having a comparator, we will be assigning a variable. So this is a node. Again, this is a node. Then we can have an input node R. Then we can have an output node C. Then from R to this is the complete path A, B. These are the nodes A, B, C, and D. So from A to B, transmittance assigned is 1. So B is this summer. So from B to this takeoff point, the transmittance is G. From this point to the output, the transmittance is 1. Obviously, I just haven't put up an arrow over here. So here we have a arrow in the forward direction. Again, we have arrow in the forward direction. Then we have to identify all the possible forward path between the input node and the output node. Input node is R, output node is C. So there exists only one forward path, A, B, C, and D. And what is associated path gain with it? That is equal to 1 multiplied by G multiplied by 1. So that will be equal to G. Then similarly, we can identify only one loop. So that is B, C to B. And its loop gain is minus GH. Then in case as there is only one loop, there is no question of 2 non-touching loop or 3 non-touching loop. This is the simplest case I have taken to get the transfer function by using the Mason's gain formula. So then get the value of delta. Delta is 1 minus loop gain of all the individual loops. There is only one loop that is having a loop gain of G multiplied by minus H. So 1 minus into minus GH. So that will give you the value of delta is equal to 1 plus GH. Then we are having one forward path that is having a gain of G, and we have to get, so because when we have to apply the Mason's gain formula, then we have to just put up the summation of all the path multiplied by the corresponding delta. So there is only one forward path P1, corresponding delta is delta 1. So numerator will consist of P1 into delta 1 and denominator will have the value of delta. Delta we have already calculated, P1 we have known. In order to get the value of delta 1, we'll take 1 minus the loop gain of all the individual loop that is not touching the first forward path. First forward path is A, B, C, D. If we do not take into account this forward path, there is no loop within the system. So 1 minus 0. So delta 1 will be equal to 1 only. Then we, in order to get the transfer function between C and R, this will be equal to P1 delta 1 divided by delta. P1 we have just calculated. This is equal to G. Delta 1 is equal to 1. So G multiplied by 1. Then divided by delta. That is equal to 1 plus GH. So overall transfer function equal to G divided by 1 plus GH. That is simply in accordance with the formula that we used in the case of the block diagram reduction, that in case we are having the negative feedback, then such type of the block can be replaced by a single block that is having a transfer function of GS divided by 1 plus GSHS. And even when we are using the Mason's gain formula, we are getting the same transfer function. So this is the way, so thus the Mason's gain formula, it is it has made up the task of getting the transfer function of a particular system quite easier, and we can use it for a number of applications. So thanks for the patience learning.